We have a great pleasure to have a next talk by Balasubramanian. He will tell us about geometric secret sharing in the model of Hawking radiation. Please, 45 minutes.
Okay, great, wonderful. So let's see. Everything is working. Good. Wonderful. So yeah, I'm going to tell you about geometric secret sharing in a model of Hawking radiation. This is work based on a recent paper. This talk is based on a recent paper with this archive number 2003 05448 with my collaborators, Arjun Kar, who is, I think, one in the audience. So all the hard questions you can ask him, and Onkar Parikar, Gabor Sharoshi, and Tomonori Ugajin. Great. So let me start out with the framing of this work. So, we've been talking about the black hole information puzzle basically since the time of Hawking. And what's the puzzle? Well, in semi-classical gravity, black holes are known to have a large entropy, and they evaporate thermally, leading to a loss of unitarity. And this is, of course, is this a puzzle or is this not a puzzle? Well, it's not particularly surprising that in a semi-classical treatment, you may find that you lose information because, well, in general, the semi-classical version of gravity does not actually know about the microstates of gravity and may indeed lose information. And we know plenty of, and we know very well now that in string theory or quantum gravity, we have examples where we can explicitly demonstrate the existence of the necessary microstates. And we know that things like ADS-CFT suggest that black hole physics should be unitary. So in that sense, it's not really a puzzle that in the semi-classical treatment of Hawking, you wind up losing information. Really, the question is, can we shed any light on where the information is stored in an evaporating black hole? And so over decades now, people have had many, many suggestions for where this could be stored. The hypothesis that people have suggested and studied before is that if you look at the radiation, then somehow the information about the black hole microstates or about what fell in to make the black hole is encoded in the quantum entanglement between the Hawking radiation and the stuff in the black hole interior. So this is an old idea, except that it's very hard to make progress on. How do you actually show anything like this is true or is even reasonable without having some sort of explicit model, let's say, of all the microstates and of the radiation? So that's been the challenge. So the somewhat remarkable thing that's sort of appeared recently in the last year is that it seems to be possible to make progress on this front in semi-classical gravity. I really find this astonishing, actually, right? And how does this go? Well, so a key lever for the investigation is the realization that a way of thinking about a large effect that arises because of this loss of okay, so very often when we talk about unitarity, lack of unitarity, recovery of unitarity, we're talking about very small, exponentially small effects in the early late time Hawking radiation and so on. But it's been recently realized, especially emphasized by Pennington, for example, that there is a large effect to worry about. That is, suppose you consider Hawking radiation and naively compute the entropy of the Hawking radiation as time passes, then you find that the entropy of the Hawking radiation, naively treated as an effective field theory entropy, that entropy will increase with time, just following Hawking's calculation. But you know that if the system is actually unitary, then at late times, for a flat space black hole, after the black hole has evaporated, there's nothing left inside. So there's nothing for the Hawking radiation to be entangled with. So somehow its entanglement entropy should go to 0. And likewise, if the radiation has come into equilibrium, we know with the fixed mass to ADS black hole, then the entropy of the Hawking radiation should flatten off. So we know these things. So that's a large effect. So the question has been, how do you recover this if you believe unitarity is recovered, then you should be able to reproduce these page curves, namely this decreasing entropy or the flattening entropy at late times. And very recently, a proposed solution, digesting a number of developments by a number of people, all of these people, in fact, down here. So a proposed solution has come about in terms of what's now being called the island formula. And the island formula goes like this. Suppose you're trying to compute the entropy of some, let's say radiation quanta, in some effective field theory. And the idea is that if this field theory is coupled to any system containing gravity, then the correct way to compute the entropy formula is you compute the effective field theory entropy, but then you need to add to it the area of an island, some sort of disconnected region that may be, or regions that may be in the gravitating part of the space. You compute their area divided by 4g Newton, and then you minimize over these regions. And so this, first glance, looks very surprising, or it looks like, well, it's answer analysis of making sure you get the correct answer. But the interesting thing is that there has been explicit evidence given from the replica trick and Euclidean gravity that a formula like this may be true. So most of this evidence has been gathered in the context of two-dimensional gravity, so JT gravity, and things of this nature. So, well, to make further progress, there are a number of questions that we would like to answer, that the community would like to answer. So here are a few. So one thing that we would like to understand is we'd like to test whether the island formula extends to higher dimensions. How do we make progress when we can't calculate very explicitly as we can in 2 dimensions? We'd like to find other ways of justifying or proving the island formula. Where does this come from? And then we'd like to see, can we, since we can do this now, can we now extend the class of questions that we can make progress on, such as maybe can we get some insight into the entanglement structure within the Hawking radiation? Can we ask questions like, can you recover part of the black hole interior from part of the radiation? Do we actually need all the radiation to recover the interior, or can we just use some of the radiation? And these kinds of questions we do want to understand because, of course, if you have an actual evaporating black hole in flat space, after it has fully evaporated, there's no interior per se to be entangled with. So all the information about what fell in to make the black hole, you know, elephants, encyclopedias, and so on, is stored within the entanglement structure of the radiation. So these questions 3, 4, and 5 are definitely interesting to try to understand. I just realized I forgot to mention that if people want to ask questions, please feel free to just go ahead, and I'll take the questions as we go along. And if I don't have time, I'll say so. But please feel free to stop me and interrupt with questions. Okay, great. So today, I'm basically going to try to go after these 5 questions in the next simplest context after ADS after two-dimensional gravity, which is we're going to set things up in the context of now. Once again, this is not moving down. Great. We'd like to do this in the setup of three-dimensional gravity. Now, three-dimensional gravity is my favorite kind of gravity. And three-dimensional gravity has many appealing features that is convenient for our purposes. Now, first of all, as you well know, in three-dimensional gravity, there are black holes. There is the BTZ black hole. And then there are other interesting objects like the multi-boundary wormholes in three-dimensional anti-de Sitter space. And that gives us a convenient playground for setting up the kinds of questions that we wish to answer. Secondly, in three-dimensional gravity, there's no local graviton. And so because there's no local graviton, we don't actually have to deal with dynamics. So the kinds of solutions we're going to look for to describe the physics we're interested in can be constructed through global identifications of anti-de Sitter space. That's very convenient. That means you can do explicit calculations of many things that you can't in even higher dimensions. Another very nice thing about three-dimensional gravity is because things are really, you know, global identifications all over the place. Even though you can do the calculations explicitly, you can also explain things very often in pictures. You just display various identifications you've done, and the physics becomes clear. So in this talk, I'm going to exploit that to explain all of our results using diagrams of the geometries that we construct. So let me describe the setup. Here is the eternal BTZ black hole. It's our familiar Penrose diagram, you know, past singularity, future singularity. This is one asymptotic region. This is another asymptotic region. As you well know, this geometry can be interpreted as a wormhole between 2 asymptotically ADS regions. This dotted green line here is the equal time section. This is on the section of on the time symmetric reflection surface, on the surface, you have a wormhole going between this asymptotic region of ADS and this asymptotic region of ADS. The geometry is actually 3-dimensional, so there's a circle everywhere, which I've suppressed, and I will frequently suppress that circle because it plays no role in our arguments. Now, I've drawn here a red line also. This red line is going to play an important role for us. This is the trajectory of a brane. So here's a brane coming out of the past horizon, sort of falling in here and coming into the future over there. So that is some solution to the equations of motion with some brain moving around in the space. The reason why that's important for us is we are going to try to set up a system in which not where we are describing the eternal BTZ black hole. So here is the time reflection symmetric slice of BTZ, one asymptotic region, another asymptotic region with the horizons separating them. So we're not going to be talking about this system, the eternal black hole, but rather we'd like to build a toy model of a black hole with some microstates. That's because we want to actually talk about a black hole with some specific microstates, which is entangled with radiation and so on. So we're going to use a trick that may be from various people, but we sort of learned it from, oh, there's a typo here. This should be Kurkulu, from Maldacen and Kurkulu, and some papers by the Stanford group. And the trick is as follows. We take the region behind the BTZ horizon, so this horizon over here, and we truncate it by placing some end of the world brain there. So the end of the world brain, just by the way, is supposed to follow some trajectory like this so that it solves the equation of motion with some source. And we're going to imagine that the states of this brain are a model of the microstates of the black hole. So you know, there's some reasonable reason to think that you could do things like this because indeed, you know, there are many black holes in string theory, which are made from D brains, in which the source of the geometry is a D brain, etc. But in any case, here is just a toy model that we think that this end of the world brain has states psi I, which represent the possible different ways in which the internal space can be organized, consistent with the thing having a total mass m. Now, in this setup, we're also going to imagine that the black hole here, Hawking radiates, and we're going to imagine that the Hawking radiation is kind of collected on a little reservoir just outside the ADS boundary. That's to separate out the radiation degrees of freedom from the gravitating degrees of freedom. So we imagine that there's a reservoir here with some weak gravity where we collect the quanta. This is also standard trick that has been used repeatedly in many of the recent works. Now, suppose that these microstates are, so we're going to imagine that the radiation quanta that come out here, labeled here by I, let's suppose that K quanta have come out, right? So that the radiation quanta I, let's suppose that they're sort of maximally entangled with these brain microstates psi I, okay? So we're going to then suppose that the state of the system is some entangled state where we have the possible states of the radiation, those are labeled by I, entangled with possible states of the brain. So we have this kind of entangled state of the radiation plus brain system. Okay, so that's the combined system. This is in 3D gravity. This is the equal time slice of our black hole with microstates modeled at the end of the world brain, and there is some entanglement between the black hole microstate psi I and the radiation I. Any questions so far, by the way? Okay, I'll keep going. Okay, so great. Okay, so what's that?
I have one question, Vijay. This is.
Oh, please go ahead.
Is there any relationship between this states of the end of the world brain that you mentioned and the conformal field theory actually that sits on the boundary of ADS tree?
Yeah, so that's a very good question. And I'm not going to give you a fully satisfactory answer. So we are going to take the states on the end of the world brain to be described as states of a CFT, which is different from the CFT that describes the ADS space. So we're imagining here that there is some CFT that's sort of sitting, the end of the world brain is described as a special CFT, which can have a central charge and so on, which is different from the dual to the anti-de Sitter space. Now, the thing that's tricky about that is our usual picture of ADS CFT is that, of course, the dual to the entire anti-de Sitter space should contain the states of the black hole also. So would it be okay if we came back to this question at the end, Spenta?
Yes, yes, of course.
Okay, so
please go. Yeah.
Okay, so we'll come back to that again. You'll see after developing some more details of the setup, you'll see what is becoming tricky about the relationship between those two CFTs.
Okay. Thank you.
And then please ask again, and we'll take it up. Okay, so great. So next, so what are we going to do? So we have this end of the world brain, and we agree that there's the states on it are entangled with the radiation. Fine. So now that means, of course, that if you were to trace over this radiation, that the states at the end of the world brain could be understood to be in some density matrix. So this is the here's the dashed line is the end of the world brain, and it's in some density matrix, because if I ignore the radiation, which I have extracted from the system into this reservoir, it is in a density matrix. So now the trick we're going to play is we're going to agree that the end of the world brain is itself described by CFT. Suppose that's the case. Again, there's some precedent for thinking that when you have D brains making the microstates of black holes, like in the D1, D5 system for Strom-Zerwafa, or indeed there are examples in anti-de Sitter space, like the various kinds of superstar black holes, where the source of the geometry can be understood to be an intersection of D brains. So in many of these cases, the low energy theory of those D brains is a conformal field theory. So we're going to take this to be a conformal field theory. Okay. And if you don't like that justification, you can think about this as a continuing toy model that's being developed here. Fine. So we take that CFT, and because it's a CFT, and we're going to take its central charge to be large, we replace the CFT here on the dotted line by its own holographic dual. Okay. So notice, so there's been some recent work by a variety of authors, Almheri, Mahajan, Maldacena, others, in using this kind of trick with the two-dimensional gravities, where you imagine you have a 2D, you have a 2D CFT, and then you do a holography for it, and then you somehow grow an extra dimension of space beyond what you already had. One thing that's very nice about this setting is, since this brain, the end of the world brain, is here also two-dimensional, its holographic dual is three-dimensional. So we can think about this three-dimensional inception geometry, as we call it, as kind of continuing on from the real three-dimensional geometry. So the real geometry of the this part of the BTZ black hole is here. This is the equal time section, so it's two-dimensional. So this, you imagine it continuing in some way through the end of the world brain into this inception disk. Now, because the brain itself was in a density matrix, we should, the inception geometry here, the dual geometry to this brain, should contain a black hole, right? So the black hole here should have an area that represents the entropy, that have an area that's equal to the entropy of the density matrix on this end of the world brain. So it'll be log k, where k was the number of quanta we had in the simple model of the entanglement with the radiation we talked about. And in effect, the evaporation protocol that we should have is that as you increase k, namely the number of quanta in the radiation, well, that means that you have more and more entanglement with the radiation. And we want to see, as you increase the amount of radiation quanta, what does the entanglement entropy of the radiation of the various systems, how does it behave, right? So that's what we want to go after. So again, I point out that in this construction, nothing requires the inception geometry to have a length scale, a central charge, a Newton constant, same as the original space. It can be whatever it needs to be the dual of the theory on the end of the world brain. This goes, this is related to Spenta's question, of course, and we'll come back to this again. Okay, so, but we're going to allow the parameters indeed of this inception geometry to be different from the real geometry, and then we've got to think about the splicing condition between these two regions. Fine, so this is our setup. So now, if I agree that I've now done holography for the end of the world brain, and somehow what happens here is that I have the BTZ black hole, the throat comes in, you go to the other side of the horizon, and then it's sort of the space sort of fills in using this black hole geometry. What I can also do is I can imagine purifying this black hole geometry by treating it as being entangled with some other auxiliary system. So I'm imagining here's the real geometry, there's the black hole, there's the end of the world brain, and I purify the black hole that would have been there by simply entangling with some other auxiliary system, which here I'm drawing like this because it's sort of entangled with the system, and I fold it back out in this manner, and then it looks like this. It looks like a long wormhole. I have the original wormhole, I truncate it at the end of the world brain, and then I add another wormhole to another auxiliary system. Now, of course, in some very natural sense, this auxiliary system that purifies the black hole dual to the end of the world brane, this should be the radiation itself, right? Because we know that the way in which the density matrix on the end of the world brane is purified is by entanglement with the radiation. So there is a sense in which, if you like, the real and the inception spaces kind of live on top of each other, right? Really, the left side of this figure, if you can see my mouse here, the left side here, this radiation boundary, if you like, really should be on this side, because, you know, the radiation is being collected on this side, on the outside, in a reservoir just outside the ADS boundary. So in a sense, these things are wrapped on top of each other, but we just sort of fold it out to make it, to be able to see it. So this is, in some sense, a realization of the ER equals EPR kind of scenario, right? We've effectively geometrized the entanglement with the radiation in this way. So one way of thinking about this is, suppose you, to the extent that you take ER equals EPR, granted that and if you take, let's interpret that to mean that if you have in large amounts of entanglement, there is in some way a way of geometrizing that into sort of Einstein-Rosen bridges, okay? So that was the case. So suppose you take the radiation, which with the end of the world brane is entangled, and remove it into a reservoir. Then in some sense, what's happening here is you wind up splitting the bulk dual. And you might think, or you might interpret this as saying, we removed all the ER equals EPR bridges between the EOW brane and the radiation and kind of put them on the left-hand side instead into the inception geometry. So it's like sort of taking the ER equals EPR bridges and kind of putting them in the other direction so they're easier to see. Okay, if that could be a way in which you know, it helps to imagine what it is that we are here trying to do. Okay, so well, how do you construct such a thing? Well, you can do this either in Lorentzian or in Euclidean version, and I'll do this in the Euclidean version. So a way of thinking about this from the Euclidean, in the Euclidean geometry, is you're really constructing the kind of folded cigar geometry. Let me explain. So suppose you just had the BTZ black hole and you took the Euclidean BTZ black hole, okay? So then suppressing the circle, which plays no role in what we're doing, the Euclidean BTZ black hole has the so-called cigar geometry. So what does that mean? You see this outer light circle. By the way, you can't see my mouse, right?
Yes.
Okay, great. So consider this outer you know, shell, the light-colored shell. So the Euclidean BTZ geometry with this angular direction being the Euclidean time would be a complete shell. So you'd complete the shell fully here, okay? So that would be the Euclidean BTZ geometry. So what we're doing from the Euclidean point of view is we're truncating a part of the geometry behind the Lorentzian horizon. So in Euclidean, so if you think in Euclidean time, so the let's say the t equals 0 slice in the Euclidean time is kind of a slice that runs down the middle here. So then if you come to the other side of the horizon, which is going to be this tip of the cigar, we sort of take out a slice of it. So that's the BTZ has been sliced off in the Euclidean geometry. Then what we're doing is we're adding on the other side of that slice, we're adding a second BTZ-like geometry, if you like, that's supposed to splice in and touch down at the end of the world brane. So we want to find a solution to the equation of motion that satisfies this condition with some brane placed over here to allow it to happen. So we're going to find a solution by imposing some sort of modified version of the Israel junction conditions. By the way, if it helps to visualize, another way of thinking about this is to look from this side, that is to say from the open side here. If you look down, you know, this outer rim will be like, say, this thing, and then you're trying to take a slice out of it. That's this brane here. You'll see this thing here is this red slice here. You remove it, and then you put another geometry, splice in another geometry there. So we're going to find a solution by imposing some modified version of the Israel junction conditions. So how do you do this? Well, you have the BTZ metric on both sides with different horizons, ADS scales, and Newton constants. This is the BTZ metric that I think we're all familiar with. We're going to impose that the induced metric is continuous across, because otherwise you'd have issues, of course, with the equation of motion. And the other continuity condition we're going to impose is that the induced stress tensor from one side, the Brown-York type stress tensor from the real side, is entirely holographic. on the inception side. So, you imagine that there's a stress tensor in the brain induced by the gravity on one side, and we say that's entirely holographic and thus controls the geometry on that side. So that's going to be the boundary conditions that we will set. You can make other choices, by the way. For example, you could have made the choice that only part of the stress tensor was holographic. Right? Or you could have made the choice that on the other side of the horizon wasn't just BTZ, but there was more complicated topology. But we'll stick with these choices because it's the simplest way to go to make progress. Okay. So I'm now about to start talking about. So we have the basic setup, and I'm about to start talking about trying to compute the holographic entanglement entropy and such in this setting. So let me pause to take any questions. Okay, in that case, I will continue. Again, please feel free to interrupt as you want. Fine, so we have our basic setup, and now let me see if I'm able, oh, great, I've now lost the, great. So what I want to do is now I have this incepted geometry, if you like. We have a way of talking about a black hole with microstates in terms of the end of the world brain. We have a way of talking about the radiation being collected in a reservoir just outside the ADS space. And we have a way of converting the end of the world brain also into geometry by just doing holography for it, replacing it with another metric, and then making sure there's some consistency conditions for the metric on either side of the brain. So in some sense, the inception geometry is a geometric representation of the black hole microstates. Great. So now we're going to make a proposal for how you're supposed to compute holographic entanglement entropy in the setting. So recall.
May I ask a question, please?
Please, go ahead.
So what would a different boundary condition look like for the stress energy tensor? If you say it was not entirely holographic, what kind of condition would you write?
Right. So what you could do is you could decide that there's some condition that tells you which part of the stress energy tensor should be holographic and which shouldn't, as you will see. So we haven't actually completely sorted that point out as to what choices of boundary conditions we may want to pick or not pick, etc. So we do not have any kind of systematic understanding of that. As you will see, the reason why I raised that possibility is that when you run the radiation protocol that we'll want to do, that is to say, increase the size of the inception black hole, its horizon area, in order to satisfy the gluing condition in the way we've set it up, you'll have to keep changing, for example, the length scale of the inception geometry. So that'll be part of the protocol, right? So you should be thinking of each of these systems as an ADS black hole in equilibrium with the radiation, and we consider more or less radiation. So it's okay to do this. But you might wonder whether you could instead pick a protocol where, for example, you could keep the ADS length scale and the inception size fixed and just fiddle with the black hole horizon area in the inception side, so namely representing how much radiation you have. If you want to do that, then you can't take, it turns out, you can't take all of the stress energy to be holographic. But I cannot tell you in, this answer would be acceptable if I could tell you, well, and the meaning of that is such and such. So, but I can't tell you exactly what the meaning of that is. We haven't sorted it out. Does that answer your question? Or does that appropriately not answer your question?
Yeah, well, I don't know exactly, but okay, maybe it will become clear later.
Okay, I think your question of what else could you do will not become clear. I think that for the moment, then we should just take it that this is what we're going to do. We're going to declare it all to be holographic.
Maybe, Vijay, can I make a small technical comment?
Yeah, who's this?
This is Arjun.
Oh, hi, Arjun.
Hey.
Arjun is my collaborator on this work, so go for it.
So I think a possible answer to the question may be, so can you back up to the slide where you showed the junction condition?
Sure. I'm having issues here. Junction conditions here.
Yeah, so I think a possible answer to your question is if you decide that not all of the stress tensor is holographic, then in this condition that equates the extrinsic curvatures of the real and inception geometries, what will happen is on the right-hand side of that equation, you'll just have some other stress tensor contribution that you get to pick. So that's the way it would be modified.
That's how you'd implement it technically. I think the physical question of what that added piece would or wouldn't mean, I don't think we have a very clear answer for them.
Yeah, that's right.
But
Okay, yeah.
If the question was technical, that's what it would mean.
Yeah, that's what I was confused about. Okay, thanks.
Okay. Thank you, and thanks, Arjun. Please just jump in, Arjun, whenever things would be clearer. Okay, we have, okay, yeah, we're talking about how to compute the holographic entanglement entropy. So recall that the standard RT prescription goes as follows. So here's the boundary A, and remember this is the inception geometry, this is the real geometry. The standard RT prescription says, suppose you want to compute the holographic entanglement entropy of this region A1 here, part of the boundary A. You find a minimal surface, an extremal surface that is homologous to A1, and the smallest extremal surface of this kind defines for A over 4g Newton would tell you the entanglement entropy. So that's the idea, right? So now the proposal is that in the context we're talking about with this inception, these end of the world brains, etc., that when you compute such extremal surfaces, they're allowed to hit the end of the world brain. And if they hit the end of the world brain, you must somehow include the entanglement entropy associated with the degrees of freedom that are on the end of the world brain. But that's part of the region of interest. And that if you have then done holography for the end of the world brain, that you just run the extremal surface into the inception region, you just run it through. But of course, there will be some sort of refraction condition imposed by the fact that the cosmological constant may be different between these two regions. You know, you have to compute the geodesic in the geometry that's actually there. And then the idea is that the entanglement entropy that you compute for, let's say, this region A1 is going to be the minimum over the total area. So that is to say, there may be a minimal surface that's just restricted to the real side. There may be another minimal surface, extremal surface that's that penetrates into the inception side. You look at all of them and you find whichever one minimizes the gives you the minimum value for A over 4g Newton, and that is the entanglement entropy. So that's the idea. And furthermore, given that this is the case, you could compute the entanglement entropy in the CFT dual to the original space, or you could compute entanglement entropy in the CFT dual to this inception space, right? So you could do either. And we're going to interpret, as I said, that these inception degrees of freedom are the radiation degrees of freedom, because the radiation degrees of freedom purified the thermal state in which the black hole microstates found themselves. Okay, so we can compute the entanglement entropy on either side, and we will tend to compute the entanglement entropy of the radiation here because that is what is pertinent for the page curve. Fine, so let's do it. So let's start. Now you'll see that if you take for granted that you can do this inception and that we agree that this RT prescription, this extended RT prescription is valid, namely your minimal surfaces can run between the real and inception geometries, all kinds of good things kind of pop out basically for free. You can look at the pictures and see what's going to happen. So here's the page transition. So imagine I've done this thing where I had the original black hole. The microstates were sort of modeled by this end of the world brain. We did holography we did inception and turned the end of the world brain into another geometry. So we have basically a long wormhole of this kind here, glued together with the gluing conditions that we discussed earlier. Now, this long wormhole has two horizons. There's this one A prime, with area A prime in the inception geometry, and this one with area A in the original geometry. Now, according to our extended Ryu-Takanagi prescription, if you want to compute the entanglement entropy of the radiation, or for that matter, the original CFT, what do? You find out you look at all surfaces homologous to the region of interest in either part of the geometry, and you pick the smallest one. So we have two pieces here, where you have the original black hole entropy, and we have the area over 4g Newton of the inception horizon, which is log k. K, remember, was the parameter counting the entropy in the Hawking quanta. And our evaporation protocol is you start with small k, so there hasn't been much radiation, and you keep increasing it so that the horizon area on the inception side increases. So then it's completely clear what's going to happen in the setting. When this quantity is small, right, the entanglement entropy of the radiation, S of R, is going to be equal to this area, A prime of 4G Newton. And then at some point, if you make this much bigger, you're now threatened with violating the page, the bound that the entropy, the entanglement entropy of the radiation can't be more than the black hole entropy. So it threatens to get big. As this gets big, and as you increase the K in the evaporation protocol. But at the moment when this gets bigger than the black hole horizon, pop, the prescription, the extended RT prescription that we're proposing would cause you to pick the black hole horizon instead as the minimal surface. So automatically the page transition will be satisfied. You basically got it for free. What's more, we can also phrase this in the recent language of islands in entanglement entropy. So suppose I'm computing the entanglement entropy of the radiation in this region R, then early in the evaporation protocol, the entanglement wedge of this region just comes up to the horizon on the inception side. So it doesn't contain any of the black hole interior. But then late in the evaporation protocol, the entanglement wedge of R includes this interior because, as I said, the minimal surface in question becomes the black hole horizon, right? So once that happens, if you think about what, if I instead wrap this surface, back to the left, right? Remember that we visualized it, the radiation to the left. It's really to the right, if you like, just outside the reservoir. Radiation reservoir is just outside the ADS boundary in some sense, right? So if you visualize it that way, then what happens is that the radiation is entangled, of course, with itself, and then also with a disconnected region, disconnected from the ADS boundary region inside the black hole horizon. That's the island that people have been talking about. So it comes out for free from the RT prescription if you agree with this idea of inception and running things in between the two regions. Okay, so you might ask, well, why should I believe this new RT prescription? And so we're going to try to give you a replica trick argument for it. So here's the replica trick argument. So remember, this is the Euclidean manifold we're talking about. This outside rim, the light colored thing, is the original geometry, and it's been spliced in with the inception geometry over there. Now so you have to imagine the cigar runs off to infinity, and that this rim here is the boundary of ADS on which the CFT lives. So I wish to compute, and remember, this is Euclidean time running this way. And so there's always a circle over each point, which I have suppressed. Suppose I now want to compute the density matrix of the radiation at, let's say, time 0. What I do is I cut this thing here over there. So that's this cut over here. And we do the path integral on either side of the cut. And that gives me, by construction, by definition of the path integral, it gives me the density matrix of the radiation. Now, suppose I want to compute the Rényi entropies. Well, what do? I take 3 copies of rho R, so I get 3 copies of this, and I splice them together cyclically. To make it easier to draw, I'm going to unfold here this branch to the left, this branch to the right, and I'm going to stick them together. These crosses match the places where I've done the splicing together. So, this is a bit cartoonish, so sort of more completely, what you want to do now is you want to do how do you compute this Rényi, trace rho R cubed? Well, you could do that in field theory. And if you want to do the holographic calculation, you're supposed to do now the bulk path integral over all geometries which satisfy these boundary conditions. And so the saddle points of these things are going to dominate the computation of the Rényi entropy, right? So in the usual holographic kind of way. So to do that, you need to fill in this boundary with a replica symmetric bulk saddle point. Okay, so I've drawn one such thing here, and I'll expand more on this in the next slide. So there are actually 2 ways of doing this. So actually, let's first look at this indeed. So what I've drawn here is, how to say this? So if you look at this, I'm filling, so imagine you're looking at this figure on the right. Whoops, imagine I'm looking at this figure from the top. Then if you look at this figure from the top, then you see the boundary is this outer rim with, you know, white bits and gray bits with a cross in the middle. So that's this boundary. And what we're drawing is in the language of this 3D shape with this sort of convex concave things, what the geometry filling in this boundary would look like. You know, there's this piece here, this piece here, this piece here, and they're all sort of curved in and out in this manner. So this is a replica symmetric bulk saddle. Replica symmetric means it has a Z3 symmetry. So in fact, in this case, it turns out that there are two ways to fill in the boundary in a replica symmetric way. So this dashed lines here are the end of the world brane. And one way of filling in the boundary in replica symmetric way has the fixed point, the Z3 fixed point, on the inception side of the geometry. And it has the page face where the fixed point is on the black hole, real black hole side of the geometry. So namely, you know, you take this boundary, the outer rim, and you can fill in the geometry in two ways. And here, once again, I've shown the visualization, the 3D visualization of this saddle point over here, right? And you can draw a similar picture for this saddle point over here. So great. So now we have two competing replica symmetric, so ZN symmetric choices for bulk manifold with which to fill in the boundary. And of course, they compete to dominate the computation. And in one phase, right, in the rising phase for the radiation entropy, the saddle on the left dominates, and on the page phase, where the entropy is supposed to sort of stabilize, the saddle on the right dominates. So here we are using, you know, insights from the Lefkowitz-Maldacena paper, basically, which shows that as the n goes to 1 in the replicas, in order to recover the von Neumann entropy, the dominant contribution to the entropy is from the area of the fixed point of the replica symmetry. So we're using that fact. So great. So here's a replica proof, if you like, of our proposed extension of the RT formula. Fine. So I'm nearly done here. I think I have a few minutes to finish. So in the last few minutes, I'm going to now, you know, go wild and apply this and do all kinds of, you know, fun stuff with this tool that we now have. So next, you remember I said that one of the questions we'd love to answer using these new tools is, what is the structure of entanglement within the Hawking radiation? Can part of the radiation allow us to recover part of the interior, you know, that kind of thing. And that's usually, you'd think that'd be very hard to do. So we're going to try to have some fun with this formalism to try to see if we can shed any light on it. So step one, so here's method one. So in this first method, we're going to split the radiation, this stuff here, into multiple Hilbert space components. So I'm going to imagine that I've split the radiation. Instead of having, you know, one big R reservoir, I have two reservoirs, for example. And here I've drawn the same picture that I was drawing before. That's, you know, it's folded in. You know, really the inception geometry goes back to the real boundary in some sense, but we'll sort of unfold it so the picture looks like this. And you have the real side, there's the end of the world brane, and then the other side, I have two reservoirs that have collected the radiation instead of one. You could imagine this, if you wish, to be R1 as, you know, early time radiation, and R2 to be late time radiation. Anyway, there are two reservoirs that have collected it. So we would like to ask the question, suppose I gave you only part of the radiation, can you reconstruct, let's say, a part of the black hole radiation with part of the radiation? Do you have sort of, if you like, partial islands and things that can develop? So it turns out you can construct such solutions explicitly, right? So the first criterion here is to be able to do this, you need to be able to construct these sort of inception geometries. So you can do that explicitly. And I'm not going to go into details about this. So it's a standard technology where what you do is you construct all solutions in 3D gravity as identifications of the hyperbolic plane. So if you take the hyperbolic plane to be the upper half space, then a way of constructing the BTZ geometry is, you know, you have this circle here, which is one geodesic and here's another circle, which is another geodesic, and you kind of identify them, and that'll give you the BTZ, you know, the eternal BTZ wormhole. So to construct this kind of geometry, which is what we were talking about before, in which you've got one real space and then you have this sort of inception space, what you do is you take two copies of BTZ, then you proceed to, so this black part here is the asymptotic region, this part and this part. Then you put the end of the world brane at some other location. This is another, so this is the brane trajectory, as it turns out, will be aligned like this. And then you identify the dashed line in this picture and the dashed line in this picture, and that gives you this long wormhole geometry that we were already talking about. For our purposes now, we need to do more complicated things. And the more complicated things are, well, you know, you've got multiple horizons, you've got multiple things being identified that in these multiple, this is just the inception part of the geometry, by the way. There's a separate part here that's for the real part. And then in this picture, the dashed blue lines turn out to be the horizons. There's a whole technology here that we don't have time to go into. Anyway, the key point that I want to point out is when you do this construction, it turns out that in addition to the minimal surfaces we already know about, which are the horizons, here's these dashed blue lines. Turns out that when you make these constructions, there is a new class of extremal surfaces you can write down. We'll call these things infalling geodesics. And in this kind of upper half plane picture, these are these purple circular arcs. You know, if you want to know details about how these things are constructed, you should look at our paper. So it turns out, so if I'm looking at, extremal surfaces homologous to this radiation region R1, you have this dashed blue line, which is the horizon of R1. You have the union of this horizon and this horizon. And you also have this purple curve. And that's going to have some interesting consequences. So we call that curve the infalling horizon geodesic. So here's what happens because of it. Suppose you run this evaporation protocol, and we're going to do it in such a manner, we're going to set it up so that the three horizons, these three blue lines on the inception side have the same size, right? That's just to keep things simple for us. So then you start early in the evaporation protocol where these horizons are all small. There isn't much radiation, right? So then it'll turn out that the minimal surface homologous to R1 is going to be this horizon here. Okay, so then the entanglement wedge of R1 just includes this region, and so it doesn't know anything behind the horizon. But then it turns out that at late times, as these inception horizons grow, as this dashed blue line becomes big, there's a shorter geodesic that is homologous to R1, a shorter minimal surface, and that's this purple line, the infalling geodesic. And then the entanglement wedge of R1 becomes all of this purple region over here, so it includes a partial island inside the black hole. So in other words, at late times, if you know everything about the radiation R1 in this picture, you will know something about the region behind the horizon, something about the black hole microstates, but you won't know everything, okay? And it turns out no matter how late you wait, if you only have some of the radiation, you will never recover the entirety of the interior. Great, that accords well with what we would hope. Here's another interesting thing. So we can draw the picture like this. So this is, we can describe this in detail in the following way. This black line is the entropy of the real black hole. This dashed blue line is the entropy associated with this horizon, associated with the first radiation region. This purple line is the entropy associated with this sort of infalling geodesic, if you like, and we're running the radiation protocol going to the right. Namely, we make the total entropy, we put more and more entropy into the radiation. So what happens is at early times, the smallest thing is indeed the horizon associated with R1. You crank things up, you keep running through the radiation protocol. At some point, you pass through the page transition. And then after you pass through the page transition, sometime after that, it turns out that this purple geodesic with the partial island is the one that dominates the entanglement entropy of R1, and thereby you get partial recovery of the interior. Now, a confusing point, I put up this picture for a reason, and that is because, look, the entropy of the region R1, which is given by this dashed blue line and the purple line, can exceed the real black hole entropy, right? And you might say, how is that possible? Well, it's because, of course, R1 can be entangled with R2. So within the Hawking radiation, in this language, there can be entanglement, which is not pertinent about the black hole interior. So basically, R1 can contain information about R2, but we don't care if we're interested in recovering the black hole interior. But this means, of course, that the entropy of R1 can be bigger than the entropy of R2, right? And that, can be big. Entropy of R1 can be bigger than the entropy of the black hole, and that's just fine. So I think I'm almost out of time, so I'm going to probably end with this snippet. So actually, the result that we've just shown points to a phenomenon of quantum secret sharing in Hawking radiation. So imagine that you have this region R1 and you have this region R2. And suppose at very late times, I take the entanglement wedge of R1, union the entanglement wedge of R2. So there are these two infalling geodesics, and the regions behind them are part of the entanglement wedges of R1 and R2. There's this region inside the black hole that is not in the entanglement wedge of either of them. So even at very late times when these two infalling geodesics just touch, you'll find that there's this, so this picture here is looking from the side A. So if you look this way towards this, you'll see a picture like this, but there is this purple blob with the black hole horizon in the middle, which is not in the entanglement wedge, is not in the union of entanglement wedges of R1 and R2. Right? On the other hand, if you compute the entanglement wedge of the union of R1 and R2, in other words, you don't take the union of entanglement wedges, but you find the entanglement wedge of the union of regions, then that you'll find is in fact equal to the black hole horizon, that you'll find extends all the way to the black hole horizon. So in other words, this points to a quantum secret sharing scheme of the radiation. An observer really needs access to all of the radiation at the same time in order to recover the full interior. So I'm out of time, I think. So I'll just flash this and say that you might worry that these findings are a consequence of this artificial procedure I followed, wherein I split the radiation into two asymptotic regions, two reservoirs, R1 and R2. And you might say, what if you had only one reservoir, but you looked at only part of it? So that's this picture where you have only one reservoir and you just take a part of it, this part of it, R, and then compute the entanglement entropy of that. And a similar secret sharing thing happens there too, and we don't have time to go into it. Great, so what did we show? So hopefully I convinced you that the entanglement island phenomenon actually does extend to three-dimensional gravity. We tried to justify that effect directly by just using the Ryu-Takanagi formula, but we had to extend it in an interesting way that allowed the extremal surfaces to pass through what we call an inception geometry for purifying the black hole microstates. Then I justified that extension of the RT formula in the context of this inception by using the replica technique. I then showed that if you agree with those constructions, that is, you can do this inception and then you can run this RT formula in this new way, then several things obtained. First is that the page transition is recovered, thus preserving semi-classical unitarity. Second thing is that the black hole interior can be partially recovered from a subset of the radiation. And third, we showed that the radiation seems to implement a quantum secret sharing scheme whereby you need simultaneous quantum access to all of it to recover the black hole interior. Great, I'll stop there.
Okay, thank you very much for your very interesting talk. Any questions, please? We have a few minutes for questions. Please use this opportunity. To learn secret, yes. Just use this opportunity to learn secret.
I have a small question. I mean, just for, can you summarize what's the ingredients of your model? I mean, you have a three-dimensional black hole and brain placed over horizon, and then main steps are, can you just make a short summary of the model again?
Absolutely. So we started with the three-dimensional black holes, the BTZ metric. You replace the geometry behind the horizon with the end of the world brain, which is supposed to be a model of microstates. Okay.
And do you use, sorry, do you use eternal black hole or just one-sided black hole? You can start with one-sided.
So this is an attempt at a one-sided black hole with an explicit model of microstates. So strictly speaking, what you really should do if you want to have a model of the microstates is, I don't know, so either you should have the D brains that are actually in there present, present in person, or you have, the appropriately souped up version of fuzzballs, something, that would be a full model, a stringy model of some kind of microstates. But instead we sort of mock it up by saying there's a brain there with some states. Okay. So then we agree that that brain is itself a CFT, and therefore we can simply replace its physics, the field theory on the brain. I can just replace it with another geometry. Okay, so we have a second ADS geometry coming out of that. So again, we had the original black hole, one-sided, with some model of the microstates, which we've turned into a second geometry. So then we needed a gluing condition for how you glue these things together, and we proposed some condition that we believe to be consistent for that gluing.
I mean, it's the Israel gluing, right?
It is what?
Is it Israel gluing condition, right?
It's almost the Israel gluing condition.
Yeah, I mean almost, yeah.
It's
Okay, and then
the remaining ingredient was saying that now that you have this extended geometry, you can legitimately do Ryu Takanagi on either side of the geometry, and the surfaces, the minimal surfaces, can pass through the interface. That we actually made some kind of argument for using the replica trick. So that, you know, you can feel some confidence about, I think. So that'll be true. So the pieces that I think require some thought and development are, well, so what does it exactly mean to sort of put this end of the world brain behind the horizon? You know, other people have done this, obviously, right? I mean, so you know, the group from Stanford, you know, you know, so this is a trick that we use standardly, but you know, one could hope to do one step better than that and having a better model. That has a bearing on Spenta's question from earlier of shouldn't the theory on this end of the E or W brain somehow be contained within the theory of the dual to the entire ADS? I don't really have a very good answer for that. There's some trickery going on here, in my opinion, involving when we remove the radiation into this reservoir just outside. It's somehow not a part of the dual to the ADS because I've removed this radiation. And so somehow that is getting tied up in the, you know, what this theory of the microstates entangled with the radiation should be. But I don't think I personally have a very clear, I don't know, I don't think I have a very clear explanation of what I think is going on there. But so I think that's loose in my opinion. Another thing that's loose is in many of these constructions, you know, we talk about this, indeed, this reservoir in which you put transparent boundary conditions and take things just outside the horizon. It would be far more satisfactory if instead, you know, we know full well that many of these ADS scenarios arise by looking at brains in flat space. So there's a flat space region attached to a throat. And here we're really talking about the geometry of the throat. So you'd rather just do that and then talk about that flat space region and collecting the radiation of the flat space region directly. So a kind of more rigorous version of all of this seems possible and would be, I think, very nice to do.
Okay, thank you.
Okay, more questions?
Yes, I have a question. Have you looked into computing the Renyi entropies for all n, including non-integer case? Because I think in your model it might be possible.
We haven't.
Yeah, so it's just Tom Hartman gave a talk earlier about their paper on the replica wormholes, and so he explained this orbifold trick in there, so that, and the picture kind of looks similar to your model. So if you take the Z, you can quotient the 3 replica geometry by the Z3 and get an orbifold, then you can analytically continue the quotient to the non-integer n slightly. And since you work in the ADS3 geometry, you can just write everything in terms of SL2R algebra. And then you can compute the geodesics also using just trace formulas from the SL2R geometry. I wonder if you...
Okay, that sounds interesting. I mean, I think that sounds interesting. I should go listen to Tom's talk and understand that better. I think anything we can do. So just to add to your comment, the recent developments are very exciting. I think they're super cool. Most of them, however, are at somewhat at the level of toy model, right? You know, even 2-dimensional gravity as a whole is some kind of toy model. Anything we can do to sort of put things in a more solid footing, as in everything is done by calculation and more in higher dimensions, etc., is very, very useful. So if that can be done, I think it sounds like a good thing to do.
Right. Also, I don't think we know yet like all possible variations of the page curves for different n. Do we? I think that's also might be interesting. Like, yeah. Okay. Thanks.
Thank you.
Okay. If no more questions, the time is over. So let's thank the speaker for a very nice talk. Thank you very much.